In this video, I want to talk about an efficient algorithm to compute log. It's based on the method we discussed in the video, how to compute log by hand. In that video, we explained the principles behind log operations. Take log 2 for example. You break down the growth into several periods, for example, 10 steps. During each step, it grows by 0.1 unit. We back out the portion that comes from the mother unit. Then we add them together as the approximation for the natural growth rate. If we do 100 steps, we will get more accurate answer. Here's how to think about it. From 1 to x, the overall growth is x minus 1. But only a portion of it comes from the starting unit. Others come from its offspring. Log operation backs out the portion comes from this one unit. Here's how. At any instant, when the overall growth is ds, only a portion of it, dr, belongs to the starting unit. The ratio of the two growth is the inverse of the size. Hence, log x can be thought of as the cumulative growth at the speed of the invert size when the size grows from 1 to x. But unfortunately, this integration doesn't have a formula result. If we were to integrate a polynomial, then we will have a nice formula result. If you have a formula result, then it's easy to compute. So the plan is to approximate this inverse in terms of polynomial using Taylor expansion. The series of derivatives are pretty predictable. Now, where to do the expansion? You can't expand at 0 because all these will go to infinity. Another easy point of expansion is at 1. These derivatives at 1 are predictable numbers. So this inverse can be approximated in terms of simple polynomials. If we substitute the integrand with this polynomial, each one can be integrated separately. S minus 1 is the overall growth. Changing the variable slightly, this integration can be done when the growth changes from 0 to x minus 1. Each becomes a power term evaluated at 2 endpoints. We end up with this series. Looking at this format, it's tempting to keep expanding and regrouping. Stop that, because you would end up with more mess. We should instead change how we look at this x. We should view the outcome x as the net growth plus the original one. Remember, the x here is the overall growth. This way, we end up with a neat series in terms of the growth. But it's never ending. So, infinite Taylor series has that runaway feature if you don't control your input x. It works well when x is smaller than 1, because in that case, the higher order term die really fast. So you only need to have a few terms to have good precision. For example, if I want log 1.5, I first convert it into a growth of 0.5. Then only use the first 10 terms, I get pretty good result. This is much more efficient than our original method. But you might ask, what if we have x greater than 1? The trick is to break up a big number into smaller numbers, for example, a number in the multiples of 2, and a decimal. The first log property allows us to compute this log product as a sum of two logs. The second property allows us to compute the log of the multiples of 2 in terms of simple scaling of log 2. Log 2 is the negative of log 1/2, and that can be computed using this Taylor series. The decimal number can be broken down into 1 plus a small number. Using the Taylor series, we're able to compute it with precision, efficiently. So this algorithm is both accurate and efficient.